The maximum entropy principle. So entropy can be thought of as a function on probability distributions. Let me explain. Here's Shannon entropy, and we can think of it as a function of variables P1 to PR with the constraints that the P's are non-negative and sum to 1. For example, a binary classifier would have a P1 and a P2. The entropy would be h of P1 and P2, which is negative P1 log base 2 P1 minus P2 log base 2 of P2. The constraint, P1 plus P2 equals 1, means that P2 is 1 minus P1. Just relabel the P1 by just P. And then our entropy, h of P is negative P log base 2 of P minus 1 minus P log base 2 of 1 minus P. That is, entropy is actually a function of r minus 1 variables because we can eliminate one using the fact that they sum to 1. Notice that self-information is non-negative, so entropy is non-negative. And what if we had p sub I as 1 for some I, which would have to force all the other p's to be 0? Well, then our entropy would be 0. And as p sub I decreases from 1, the surprisal increases. So entropy is a measure of disorder. If an event always occurs, its entropy is 0. But if that event becomes more uncertain, its entropy is positive and increases with the event's uncertainty. Well, that's intuitively, but we can only go so far with intuition. Let's look at the math. The math is convexity. So here's our definition of a convex function from Rn to R, or a subset of Rn to R. The sum of the p sub I x sub i's equals p1 x1 up to pr xr. That's called a convex linear combination. And if you have a negative convex, then the function f itself is said to be concave. And there's a nice little theorem. If you have j equals 1 to m convex functions, then any convex combinations of the f sub j is also convex. It's a good exercise, like on a midterm or a final. So what about just ordinary functions of one variable? Well, convex means curving up with respect to the horizontal. And concave means curving down with respect to the horizontal. So if we only have two labels, then convex means f of the quantity p1 x1 plus p2 x2 is less than or equal to p1 f of x1 plus p2 f of x2. So let's look at a diagram. This line is a secant line, and it plays an important role because if we have a convex combination, it's between x1 and x2. The function value is less than or equal to the convex combination of the function values. That's the definition of convexity. Also, if f is differentiable, then the graph of f of x is above each of its tangent lines. So if f is continuous and convex on AB, then it actually has a unique minimum. So min here stands for minimum. We can see the minimum here is at A, and A is called the argmin of f. So here we also have a minimum, but it's at some C, which is the argmin of f. And notice that the gradient of f at C is equal to 0. And the gradient's what we usually call the derivative. So here's another example of a minimum, but in this case the argmin is an entire interval. And here the argmin is also an entire interval. So there are theorems and proofs which you could learn in a course on convex optimization. We're not going to look at them here except for one very important theorem we look at next. If the second derivative is positive and continuous on an interval of R, then f is convex on that interval. The proof uses Taylor's theorem, which says there is some C in that interval, such that f of u equals f of v plus f prime of v u minus v plus 1/2 f double prime of c u minus v squared. But that f double prime of c is positive, So we have a non-negative final term, which means that f of u must be greater than or equal to the sum of the first two. Let v be equal to a convex combination of x sub i's, where x sub i's are a subset of AB. V, therefore, is in AB. And notice that we can rewrite our Taylor's theorem result and then form convex combinations. We can factor out an f of v, but then we've got an I equals 1 to r of p sub I, and that adds up to 1. So that's just f of v plus f prime of v, and we split up the difference in the final sum, and now we have I equals 1 to r p sub I x sub I, and so we get f of v, but v is equal to I equals 1 to r p sub I x sub I. So f of v plus f prime of v. And the sum I equals 1 to r of p sub I sums to 1. So that's minus f prime of v times v, or just f of v. So we've shown this convex combination of f of x sub i's is greater or equal to f of v, but v is itself a convex combination. And therefore we have our theorem. So h of x turns out to be concave, which means its negative is convex. Why? Well, if we look at the function negative p log base p of p for b greater than 1, our surprisal function, remember this is how we define arbitrary logarithms, the second derivative is less than 0. Therefore, the negative second derivative is greater than 0, and therefore the negative function is convex. We had a theorem: if you have a convex combination of convex functions, the result is convex. And notice that entropy is the negative of a convex combination of convex functions. And therefore, if negative of entropy is convex, then entropy itself is concave. And concavity means that we have a maximum that's unique if a maximum exists. So Occam's razor says use the simplest model that sufficiently explains the data. There are infinitely many models. Most are very highly complex, and very highly complex models are inaccessible, they're unknowable. So models learned from data that predict probabilities should select a best probability distribution, and Occam's razor says the best model maximizes the uncertainty not represented in the model. That gives us what's called the maximum entropy principle. The best model is the one that allows the most uncertainty from the data. So a probability distribution should assign an unbiased, non-zero probability to every event not excluded by the given information. Information is going to drive our models. Intuitively, we're saying that anything we can't explain with the data is allowed to have as much uncertainty as possible. So let's look at, for example, at two outcomes, which would have a probability of p or 1 minus p. The entropy is a function of p, and as a function of p, it reaches a maximum when p is equal to 1/2. Therefore, a fair coin is the most random or has the maximum entropy process with two outcomes. But there are always constraints. Constraints are equations, inequalities, conditions on the variables in the entropy function. For example, the sum of the variables has to be 1. And also they have to be non-negative, but we won't use those as constraints. We'll just say they define the domain of entropy function. Constraints are often equations of the form g sub j of the variables is 0. And that means we often define a brand new function called the Lagrangian, which is the entropy plus new parameters, lambda 1 to lambda c, as a linear combination of the g1 to gc. Or we just substitute from the equations directly into h, and that'll be our preference when we can get away with that. So suppose the process has three outcomes: red, green, and blue. So we'll let p be the probability of red, q be the probability of green, but notice the probability of blue is 1 minus p minus q because the three probabilities sum to 1. So this is our entropy. So let's notice that as a surface, we can definitely see a maximum, and it occurs at 1/3, 1/3, which is, if you remember, 1 minus p minus q is the other probability, which is also 1/3. So if we don't know anything, and there are three possible outcomes, then the least bias, the one that allows the most uncertainty, is a probability of 1/3 for each of the outcomes. But suppose we know that the probability of green is 1/2. In other words, q is equal to 1/2. If nothing else is known, then we would assume that the least biased, the maximum entropy model, assigns probability of 1/4 to the other two outcomes. And this is in fact the model we get from the maximum entropy principle, as we'll now see. So suppose it is known that the probability of green is 1/2. In other words, q is equal to 1/2. Our entropy, with q equals 1/2 substituted, is given by this, where instead of 1 minus q minus p, we now have 1/2 minus p. The derivative, recall definition of arbitrary logarithms, and the derivative of log is 1 over p, the natural log. And here's our derivative using the product rule. Notice we can cancel the p's, cancel the 1/2 minus p's. We get a minus 1 over log 2 plus 1 over log 2 that cancels and gives us our derivative is negative log base 2 of p plus log base 2 of 1/2 minus p. The derivative is 0 when log base 2 of p is equal to log base 2 of 1/2 minus p, or when p is equal to 1/2 minus p, which is 2p equals 1/2, which is p equal to 1/4. So maximum entropy model means maximum uncertainty for those parts of the process which are unknown. The entropy, for example, was maximized at p equals 1/4 in this example. If it's known that p probability of green is 1/2, and that's all we know, then the unknown should be as uncertain as possible, which means the probability of red is the probability of blue is 1/4. This has important consequences. Many of our models will be developed using entropy. Entropy can be used to classify patterns. It can even tell us when there are no patterns. Maximum entropy is going to give us our best probability distribution. And we'll obtain best probability distributions via information, not randomness, implying that a probability is probably better thought of as a Bayesian belief or confidence. And in fact, any number between 0 and 1 that we encounter, we're likely going to call it a probability, even if it's a proportion or a relative frequency. But even when using the, quote, concept of probability, just keep in mind our true goal in context is information.